Hi everyone, Mrs. Below here. In this video, I'm going to be going over the Gay-Lussac's law notes. All right, so like we've been discussing so far, we've been talking about gases, and specifically we've been focusing on pressure, volume, and temperature. And what happens when we keep one of these variables the same or constant, then what is the relationship between the other two variables? So remember with Boyle's law, the temperature was kept the same, and we saw the pressure when the volume would increase, the pressure would decrease, and vice versa. Okay, and for Gay-Lussac's law, this time we're going to be focusing on what happens if the volume stays the same. Okay, and then we're looking at the relationship between pressure and temperature. This is probably one of the most intuitive laws for students to understand. Okay, so again, this is going to relate pressure and temperature. All right, so in figure 1 and 2 over here, you can see that they have the same volume. Both of these are fixed containers, meaning they're containers that will not change in size at all. We will be doing a lab actually using a Erlenmeyer flask on Monday. So we are manipulating the temperature and seeing how the pressure responds to that. So as the temperature changes, we're going to see changes in the pressure. So if we look over here at figure 2, we can see that that temperature is much higher than that of figure 1. Okay, so this flask has a higher temperature than this flask here. So we can see as temperature increases, okay, so we heat something up, okay, we can see that these particles, they're going to move faster, and they're going to hit the sides of the container more often, okay? Well, if the molecules are hitting the sides of the container more often, then that's also going to increase the pressure. And not only are we assuming the volumes being kept constant, we're also assuming the moles, or the amount of the gas, is being kept constant as well, so there are no gas particles entering or escaping the container, in this case, the flask. So again, like I said, this is the most intuitive thing for students to understand. As I increase the temperature of something, I'm going to also increase the pressure. And that is true when the container has a fixed volume, so the container cannot change in size, and then there's no gas particles like entering or escaping the container. So remember, Boyle's law was a little bit different because the relationship was what we call inverse, versus this is called a direct relationship. And I'll get to that in one moment. But just to summarize an explanation of what is happening. So if the volume is kept constant, that means the size of the container does not change. So it is a fixed, we could say a fixed volume. And the amount of gas is staying the same, the moles are the same, the atoms, molecules are not entering or escaping the container. Then so let's start with, if the temperature, the speed of the molecules, their kinetic energy decreases, this means the pressure would also decrease because the gas would be hitting the sides of the container less often. Versus if the temperature increases, this means the pressure would also increase because the particles would be hitting the sides of the container more often. So like I said in the previous video, we're going to use arrows to represent the speed of the molecules. Up here, the arrows were kind of the same, but you could see clearly in this one more molecules are moving around. To make things a little bit more clear, if you have a short arrow like this, that means that the molecule is moving slower and therefore it has a low temperature because it has a low amount of kinetic energy. Versus if you see a longer arrow in comparison, that means that this molecule is moving fast, so it is at a higher temperature. Okay, so remember, the longer the arrow, that means represents that the molecule is moving faster and therefore would have a higher temperature. If the arrow is shorter in comparison, that means that the molecule is moving slower and therefore would have a lower temperature. So just keep that in mind when you're looking at any diagrams moving forward. So Boyle's law was what we call an inverse relationship. Okay, because as the pressure went up, as the volume increased, the pressure decreased, and as the volume decreased, the pressure increased. Okay, that's called an inverse relationship. However, Gay-Lussac's law, this is what we call a direct relationship, because as one variable goes up, so does the other. As one increases, so does the other. As temperature goes up, pressure increases. As temperature goes down, pressure goes down. So this is the formula now that we are using for Gay-Lussac's law. P1 and T1 will represent your initial pressure and temperature, while P2 and T2 will represent the final. So again, we have conditions at a starting point, we make a change, and then what are those conditions after that change? Remember, Boyle's law, because it was an inverse relationship, this is how we represented that equation. But now we're working with a direct relationship, so this is how we're going to represent that equation. All right, again, like I said, P1 and T1 are the initial conditions. Okay, again, make sure you're getting, if you have two variables, make sure, okay, this is the situation at this point in time. Those two variables go together. And then P2 and T2, there's been some type of a change. Now we are going to look at those conditions afterwards. So it's really important is, yes, you have to make sure the units are the same like we talked about with Boyle's law. In this situation, we just had to make sure that the units were the same. Like both pressures could have been in ATM. Both pressures could have been in KPA. Both volumes could have been in milliliters. Both volumes could have been in liters. Okay. However, with temperature, it's a little bit more important because whenever you are working with temperature and using these equations, you always have to get the temperature into Kelvin, because this particular equation was based on the Kelvin scale. So if you are ever plugging in temperature to these equations, you better make sure that it is in Kelvin. The pressure, it doesn't matter, unless you're trying to find a specific pressure for your answer. And of course, you have to make sure that both pressures are in the same unit. But that doesn't really matter when plugging it in. They could both be in ATM. They can both be in KPA. However, when it comes to temperature, you can't make both of these degrees Celsius. That won't work. You have to make both of these, you have to make sure they're both in Kelvin. And you can always convert before and after plugging in back and forth between Kelvin and degrees Celsius.